It is my pleasure today to open eighth Skorokhod Readings. This meeting is organized due to memory of Anatoly Vladimir Skorokhod, one of the prominent mathematicians of the 20th century, who created, for example, not only, but for example, theory of stochastic differential equations. And he always paid a lot of attention to teaching of a new generation of mathematicians. He created a lot of activities devoted to young mathematicians of different ages, from schoolboys, students, and PhD students. So we are trying to continue his tradition, and we create such meetings, which are regularly one time in a year, in order to attract young people from different countries, to give them possibility to make talk devoted to their own mathematical investigation in the field of the stochastic process and probability. Most of the speakers on previous Skorokhod readings became to be a probabilist and participate our seminar Malyavian Calculus and Applications. So I hope that this year we will also see a new talk, new participants, and I wish success to everybody who participated this our small conference. It is my pleasure to announce the first speaker today, Alina Misnik from Kyiv Polytechnic Institute, with the talk of analysis of random walks on the hypercube. Please.
Yes, one moment, I'll share the screen. Good day, everyone. Let me briefly introduce myself. My name is Alina Misnik. I am a master's student at the Faculty of Physics and Technology at Igor Sikorsky Kyiv Polytechnic Institute in Ukraine. Today, I am honored to present the result of my research focused on the analysis of random walks on a hypercube. In modern research on probabilistic processes, increasing attention is devoted to the analysis of complex stochastic models defined on large-scale graphs. One of the most universal structures for such modeling is the hypercube, which enables a precise formalization of random walks in discrete high-dimensional spaces. The hypercube naturally represents systems with binary states and is therefore widely used in problems where the configuration of the system can be encoded as a bit string. These structures not only provides analytical tractability but also allow for efficient implementation of simulations, which is crucial when studying the behavior of large-scale stochastic systems. Because of these properties, the hypercube frequently serves as a foundational model in probability theory, complex theory, and cryptography. In particular, random walks on the hypercube have recently received significant attention in the context of time-based authentication protocols, where the security of the schemes is based on the computational difficulty of predicting the evolution of random process. The idea is that a legitimate party who knows the law governing to random walk can respond to a challenge quickly when an adversary lacking this knowledge would require significantly more computational and temporal resources. In this context, the meeting time of two random walks become a natural measure of proximity or convergence the stochastic processes. Analyzing this moment provides insights into how quickly trajectories synchronize, which can be interpreted as a mixing threshold for models with a common evolution. Such insights are valuable for assessing the cryptographic robustness of protocols that rely on unpredictability in discrete stochastic dynamics. Additionally, it is worth noting the connection between random walks on the hypercube and urn models. Both can be described in the framework of discrete time Markov chains. The evolution of the distance between particles can be represented as a transformation for generalized urn processes, where states change based on matching or mismatching coordinates. This analogy enables the application of a classical method from the theory of occupancy schemes and Markovian compositions, offering an alternative probabilistic interpretation and analytical toolkit for studying convergence and fluctuation on high-dimensional spaces. Let me begin with definition of the hypercube. A d-dimensional hypercube is a graph whose vertices are all binary vectors of length d. Two vertices are connected if and only if they differ in exactly one coordinate. A simple random walk on the hypercube in discrete times means that at each step a particle moves to one of the d adjacent vertices with equal probability. Now imagine that two particles move independently on this hypercube, each performing its own random walk. Our goal is to define a joint movement rule that will bring the particles together as quickly as possible. We propose the following rule. At each time n, particle y moves randomly to one of its neighboring vertices, following a standard random walk. Particle x, however, adjusts its movement based on the trajectory of y. Specifically, if at time n plus 1 particle y flips a coordinate where the two particles agree, then particle x flips the same coordinate. If y flips the coordinate where their values differ, then x instead flips a randomly chosen coordinate where the two particles still disagree. This rule ensures that the Hamming distance between the two particles either decreasing by 2 or stays the same at each step. It was proven that this strategy is optimal in the sense that it minimizes the expected distance between the particles after one step. This joint movement of particles can be reinterpreted as an urn model. For example, if we consider a hypercube with d equal to 100 dimensions, it can be modeled as an urn containing 100 balls of 3 different types. Each ball corresponds to one coordinate of the hypercube. A black ball means that the coordinate equals 0 for both particles. A yellow ball means both particles have 1 at that coordinate. A bicolored ball reflects a mismatch, that is, one particle has 0 and the other has 1. At each step, one ball is drawn at random. If it is black, we replace it with a yellow one, and vice versa. However, if we draw a bicolored ball, we draw another random bicolored ball and replace the pair with two monochromatic balls of either type. As a result, the number of bicolored balls either stays the same or decreased by 2. In the accompanying video or matrix, you can observe how the urn changed after one iteration of this process. The goal of the algorithm is to make the two particles meet, which corresponds to a complete disappearance of bicolored balls. That is, all coordinates match. These representations illustrate a clear connection with urn models and show how the process of transferring balls in an urn can be equivalently viewed as a random walk on a hypercube. Such reformulation provides analytical advantages, allowing the use of standard tools from the theory of random walks to study these processes. We define UN as the Hamming distance between particles x and y at time n. That is the number of coordinates where they differ. It has been proven then the sequence UN forms a Markov chain in the finite set from 0 to d, with the transition probabilities shown on the slide. Importantly, state 0 is absorbing, meaning that once the particle meet, they remain together. Moreover, the process reaches this absorbing state with probability 1, which implies that the particles will meet after a finite number of steps. Assume that d equal to 4m, so that the initial distance between the two particles is u0 equal to 2m, meaning they differ in exactly half of their coordinates. We are interested in computing the probability that the distance change from 2m to m minus 2j after n steps. This defines the probability distribution function for the particle distance. For arbitrary n more or equal to j, we derive an explicit formula for this probability as shown on the slide. The derivation is based on the method of generating functions, which provides a compact way to encode the entire sequence of probabilities. By applying the law of total probability and solving the resulting recurrence relation, we obtain the closed form expression for the distance distribution. This result is a case step to analyze the full evolution of the Markov chain that governs the particle distance, and it sets the foundation for asymptotic analysis and further probabilistic estimations. We denote Tm as the meeting time of the two particles. That is the first time when Hamming distance between them becomes 0. We assume that the process starts at a distance u0 equal to 2m, and the dimension of the hypercube is d equal to 4m. In terms of associated Markov chain, this corresponds to the first heating time of state 0, which is absorbing. The key observation is that the event UN equal to 0 is equivalent to Tm less than or equal to n. Hence, using the formula derived earlier for the distribution of the distance for j equal to m and n greater than or equal to m, we can compute the cumulative distribution function of Tm. To obtain the probability that the meeting occurs precisely at time n, we take the difference between the probabilities that meeting has occurred by time n and by time n minus 1. Substituting the known expressions and simplifying, we arrive at the theorem states on the slide. This result gives us the full distribution of the meeting time under the condition that the particles initially differ in half of their coordinates. The meeting time Tm can alternatively be expressed as the sum of independent geometrically distributed random variables. Each random variable, tau mi, corresponds to the number of steps between the i-1s and i's changes in the distance between particles. The probability of success pi is the probability of falling into a set of indices in which x and y differ, provided that the distance between them equal to m minus I minus 1. Using this geometric interpretation and the independence of random variables, we can compute the expected value and variance of the meeting time directly. The expressions are shown on the slide. They involve the harmonic number hm, and also with these values in hand, we can apply Chebyshev's inequality to show that the meeting time concentrates around its mean value. Specifically, the meeting time normalized by 2m natural logarithm n converges in probability to 1 as m tends to infinity. This result confirms that with high probability the meeting will occur close to the asymptotic average. We can also apply Chernov's inequality to estimate the probability that the meeting time Tm significantly deviates from its expected value. The general form of the inequality and the specific bound derived for our model are shown on the slide. This bound provides an upper estimate for the tail probability of deviation. Although such estimates are useful, they tend to be rather loose. For instance, with delta equal to 1 and for hypercube of dimensions d equal to 100, the bound evaluate to approximately 0.98. This illustrated that the inequality gives a bound that is close to 1 and thus may not be very informative in practical scenarios. Nevertheless, it gives us a way to theoretically control large deviations and confirms that such extreme outcomes are relatively rare. The exact value of the bound depends on the choice of delta and decreases with large deviations from the mean. This slide presents the limiting distribution of the normalized meeting time as the dimension parameter m tends to infinity. It has been shown that the normalized meeting time converges in distribution to the logarithm of an exponentially distributed random variable with rate 1. The proof relies on the method of characteristic functions. By analyzing the characteristic function of normalized random variable Tm with bar and showing its convergence to the characteristic function of minus 2 natural logarithm t, which is gamma function 1 minus 2 it, we obtain the desired result. According to the continuity theorem, this convergence of characteristic function implies convergence in distribution, thus justifying the theorem. In this part of the study, we performed a simulation using a 100-dimensional hypercube. A pair of particles performing random walks starting from two vertices of hypercube then that differ in exactly half of their coordinates. They then moved step by step according to the previously defined optimal coupling rule, and the process continued until they met. We repeated this experiment 1,000 times independently and recorded the number of steps needed for the meeting in each case. The results are shown as a normalized histogram on the right. As we can see, the shape of the empirical distribution almost perfectly matches the theoretical curve. Thus, the results of the numerical experiment agree with the theoretical conclusions. This study analyzed the joint behavior of two particles performing random walks. We proposed a coupling movement rule that is optimal in terms of minimizing the expected distance per step. The evolution of the distance between two particles was shown to form a Markov chain. We derived the corresponding generating functions, calculated the exact distribution of the distance, and examined its asymptotic properties. Furthermore, we constructed a full probabilistic description of the meeting time. We found its expectation, variance, exact distribution, and limiting behavior. We provided convergence on the meeting time both in probability and distribution, and we applied a large deviation inequality to estimate rare events. The practical accuracy of the theoretical estimates was confirmed through numerical experiments. In particular, after 1000 simulation with a fixed hypercube dimension d equal to 100, the relative error between the theoretical and empirical meeting time was approximately 1.44%. This demonstrated that the analytical approximation for the meeting time remained accurate even in finite dimensions. The shape of the empirical distribution also closely matched the theoretical one, which shows consistency with the constructed model. Possible direction for future research include extending the model to cover dependent random walks on groups, studying the asymptotic behavior of system of interacting particles as the number grows without bound, and performing a deep analysis of how to obtain result can be applied to cryptographic problems where timing characteristic of random processes are of fundamental importance. This concludes my presentation. I sincerely thank you for your attention.
Thank you very much. Maybe somebody have questions or comments, please.
Well, I have, first of all, thank you for a very nice presentation. So my first comment that the sum of geometric variables which you have found is appearing in connection with the coupon collectors problem. And I have m types of coupons, and you draw until you see them all. And the limit distribution which you identified is known as Gumbel. This is one of the classic extreme value distributions with precisely the characteristic function which you have found. So my question is whether you see some connection between your random walk model and coupon collectors.
I didn't know for this model earlier.
I see. Okay, thank you.
Maybe some other questions, please.
Maybe one one more remark about what Alexander has said. Exactly, it is related with coupon collector problem, and there is just recent paper, maybe of 25 of this year, where the rate of convergence in your limit theorem were obtained by Stein method, of course. And actually, if I am not wrong now, in terms of Wasserstein distance. So it is also interesting for your topic, because actually you have even rate of convergence in your limit theorem. Thank you.
Thank
you. Okay. Other comments, please? I have a technical questions. You only start with the initial deterministic position for particles where the distance between them is exactly 1/2 of total number.
Yes.
Coordinates. Can you do something the same if you just independently choose coordinates, choose the starting positions from all possible?
As I understand, it don't affect the result, but there is such cases that should be concerned more precisely. So I study only this one case.
I see. Okay. Maybe if there are no other questions or comments, we have to thank to our speaker, Thanks, Alina, very much for your interesting presentation. And we have to wait now 5 minutes up to the next talk. Okay, let's continue our work today. And next speaker is Oleksii Galganov from National Technical University of Ukraine with the talk Scaling Limit for Small Blocks in the Chinese Restaurant Process. Please, Oleksii.
Hello, everyone. I'm Oleksii. I'm the first year's PhD student in the Igor Sikorsky Polytechnic Institute. And my today's talk, Scaling Limit for Small Blocks in the Chinese Restaurant Process, is based on a recent joint work with Andrei Illienko. Let me start with a recap from the Skorokhod Readings of year 2022, where I was presenting my work as a recently graduated bachelor student. And on the last slide in this presentation, we mentioned two main perspectives for the further research. And the talk itself was about a limit theorem for a point process where the atoms placed in the points correspond to fixed points of a unit's random permutation. And we mentioned that the first obvious generalization would be to try doing the same for cycles of fixed length. And another one was regarding functional limit theorems. When we, for example, want to drive limit theorems for a number of fixed points, in this case, in the units permutations of different steps of different sizes. And here we mentioned that it can be done by the means of the Chinese restaurant process. And today, I will cover both of the results that we mentioned 3 years ago. And the first one was the results of my master's thesis. And the latest one is the results of this recent joint project that I mentioned earlier. Let's start from the very beginning of the origin of all this research of random permutations. There's a famous problem by Demon Moore about randomly distributed heads. And it's well known that if in this problem, if we want to calculate the limit of the probability that no one received their own head, we will get something very interesting where we with Euler's number E. And if we try to generalize it to the probability of that exactly m out of these people will receive their own heads, we will see something very intriguing because we'll see something closely connected to the Poisson random variable. And if we express it in precise terms, that if there is a uniform distributed random permutation on an integers, then the vector of all of cycle counts, like the number of cycles of length 1, length 2, and so on, it jointly converges to a vector of independent Poisson random variables, which is a known result and very old result. And actually, it's not only for uniform permutations. The first and most natural candidate for next studies are Ewan's permutations, where the probability of each permutation is proportional to some parameter in the power of number of cycles in this permutation. These permutations stem from celebrated Ewan sample formula, and the analog of this previous result is also known for permutations, but in this case, the limiting variables now have distribution which depends on the parameter of this distribution of permutations. So these results, all of them clarify the asymptotic of short cycle counts, which is basically an arithmetic results. But we wanted to study geometry, so the asymptotic cycles composition. We can define a point process which will encode all these small cycles. So this really at first sight it's a pretty weird definition, but it turns out to work out very well. So we can take the student's distributed permutation for each short cycle. We put a point in this multi-level space, and turns out that this point process actually converges in distribution to the homogeneous Poisson random measure on the same space. So actually, it's only a partial case of our results in this work, because here we mentioned a slightly more general model where permutation have...
Excuse me, can I have a question here? Because you say that psi n converge in distribution to psi, where psi is a homogeneous Poisson random measure on X. What does it mean precisely? Because X is not very simple space, as I must say. So what does it mean that psi is a homogeneous Poisson random measure here?
So yeah, in this case, the crucial thing is to define the analog, let's say, of Lebesgue measure on the space, and the way we define it. So let's say if we pick some set in the space, the measure of the space would be the sum of measure of this set intersected with, for example, this level 1, level 2, and so on and so forth. So basically, these sets in the space are the unions of usual Lebesgue measurable sets on different levels.
And then you use this Lebesgue measure multiplied by theta as the structure method for this Poisson random measure, yes?
Yes, that's correct. So that's basically which corresponds. So the interesting...
Also, for a moment, let me... can you show the previous slide? You say that you can endow the X with the matrix that turn X into Polish space. Then you use Wagner topology. It is based on the continuous function with bounded support. But it can happen that, for example, you define two different distances on X, which both give us Polish space. Can it happen that one distance is such that X is unbounded, another that X is bounded and still Polish? Then maybe all F becomes to be continuous and bounded. Maybe you can specify the distance on X, which you use.
Yes, so we define distance in, let's see, the most natural way, where if we take two elements of the space, if they're from the same level, then it's just usually Euclidean distance between these 2 points. And if they're not, let's say if one is from the level K, another from the level M, then we define the distance between these 2 points at the square root of max of K and M. So just to guarantee that the triangle inequality holds. So in this case, bounded sets are precisely the sets which lie in a finite number of levels.
I see. Okay, thank you.
So, but the main interesting about this point-process limit theorem is that we can use continuous mapping theorem to obtain limit theorem for a wide range of statistics. And we give a few examples here, like for the sum of fixed points, for some statistics related to largest fixed point, to the spacings between them, or to what we can call a range of a cycle as the difference between max and min elements. And for all these limit theorems, the only thing which is required to prove is to prove that the corresponding mapping is continuous from the space of point measures to R or some power of R. And we can go that we only prove that, and we get a limit theorem for random variables that otherwise would be really hard to prove that they converge to something and obtain an explicit form of its limiting distribution. But now let's move from statics to dynamics. So as I said, our next goal was to derive functional limit theorems for stochastic processes where we, let's say, fix the length of the cycle we want to look at. and let time to be dynamic. So we want to look at cycles of length 1, let's say, at the moment n, and the moment 2 times n, and as well as other functional characteristics.
Excuse me, you said that this sigma nt, this means that maybe these random permutations are related to each other when we have different indices. Is it true?
Yes, exactly. So it's not really interesting to look at independent permutations. So we want some dependency between them. So we need, as the first step, we need to construct all these permutations of different size on single probability space. So we need to generate them sequentially in some way. Such algorithm exists, and the simplest as it's most widely used is the algorithm known as the Chinese restaurant process. Let us describe it briefly. So imagine there's a restaurant with infinite number of large circle tables. The first guest takes a step at the first table. Second starts a new table with probability proportional to theta, or otherwise sits at another table clockwise at the same table as first guest. Then just continue, and same for any following guest. So it either starts a new table with probability proportional to theta, or sits to an already occupied table. And each table, in this case, defines a cycle in the permutation, and it will know that the permutation at step n follows the unit distribution. So this Chinese restaurant process can also be adapted to be a partition valued process rather than a permutation valued one. In this case, we discard the order of guests in each table, and in this setting, each table is a block in partition of a block in a partition of integers up to size n. So how to describe the structure and dynamics of small blocks? We know that growth of each block is described by the following scheme. So when first it's a block of size 1, then it evolves to a block of size 2, then eventually to a block of size n plus 1, and so on and so forth. So let's define the random event that shows that some block up to some fixed time k n plus 1 evolves exactly as described in the scheme. And by Borel-Cantelli lemma, each block will almost surely grow infinitely. So if we fix some integer n, capital N, and track all blocks up to the times when they reach size n plus 1, when we call them they become large, then it uniquely, all such events, they uniquely determine the structure and dynamics of such blocks. And equivalently, we can describe this by a random point measure, where we place the atoms of this measure to the n plus 1 dimensional points corresponding to the event we have here. So now we can formulate our main theorem. So first introduce a cone like this in n plus 1 dimensional Euclidean space. We can consider it as a measurable space equipped with Borel sigma algebra and the measure m defined like this. And also we need to define the localized ring of bounded sets, because if you see the measure which we define isn't bounded in the neighborhood of 0. So in order to work with that convergence correctly, we need to focus only on the sets where which, let's say, bounded away from 0 and which have finite measure. So we define our sequence of point measures by scaling point measure I mentioned earlier. So and our main results is that this sequence of point measures xi n regularly converges in distribution to the Poisson random measure on this cone with intensity measured n we defined, which is really interesting because it's obvious to expect some inhomogeneity here, but surprisingly, it takes a really simple form in this case. It's also interesting that the measures for a different n are consistent in the following sense. So if we take some set in the cone xn, extend it to be a subset of a cone for some m greater than n, then their measures are the same, and hence the distributions of these limiting point processes are also consistent, which is interesting because it agrees with the consistency of permutations we get in from partitions we get in from the Chinese restaurant process. Also, limiting processes are scale invariant, so it easily follows from the scale invariance of the intention to measure mu-m. Let us also give a brief outline of the proof. In our case, sufficient conditions for where convergence follows from some general results, like, for example, given by Kallenberg, and take the following form. So we need to provide that the limit of mean value of the expectation of value of this process on some, let's say, nice sets converge to the value of measure mu on these sets, and the void probabilities also converge to void probabilities of our Poisson random measure. And we need to prove it for all the sets U that are, for example, are finite union of closed convex sets in our count X set. And the key step is driving the asymptotics for the joint probability that we have our cycles that develop according to the scheme we mentioned above. Again, this results, when combined with the continuous Pepin theorem, can lead us to limit theorems for a wide variety of statistics. But now, apart from classic limit theorems, we can also derive functional ones in the Skorokhod topology. So let's start with the classic one. So as I mentioned earlier, it's known that the joint distribution of cycle counts in a permutation at one step converges to independent Poisson random variables. But now we can derive similar results, but for a joint distribution of all cycle counts, let's say at permutation of size n and permutation of size alpha n. So for example, cycles or blocks of size 3 at step n, and blocks of size 6 at step 210. And in this case, we obtain the limiting distribution in explicit form with a family of independent Poisson random variables. Another example, let us consider the number of blocks of size k at the step nt. Functional limit theorems for this stochastic process was studied by Gnady and Stark recently. And in the limit, there is a certain time-changed continuous time stationary Markov chain arises. And our previous theorem provides actually an explicit construction of the limiting process. As an example, let us restrict it to the case of K1, so singletons. So according to the work of Gnady and Stark, this stochastic process converges in distribution to a sometime changed version of stationary Berthon-Tess process. But from the perspective of our result, the limiting process is just the value of this Poisson measure on some infinite rectangle, so like this. So as at time t2 there are 4 atoms, and time t3 there are 2. So we just count the number of points of this limiting process in this moving rectangle. And also, this explicit construction allows to express the finite dimensional distributions of this process in terms of multivariate probability generating functions. And in other words, these finite dimensional distributions are multivariate distributions, discrete distributions with dependent Poisson measurements. We can also derive limit theorems for much more involved block statistics for beyond block counts. Another example is the first singleton at the time nt. In this case, we obtain a limit theorem in the Skorokhod topology on half-real line to some almost Chern decreasing process with explicitly defined final dimensional distributions. And this process, again in our notation, if we take the rectangles like this, then the value of this process at let's say time at some fixed time would be the x-coordinate of the leftmost atom in this rectangle. So as a slightly different example, let us turn to singletons with short lifetime. Here, we must exclude singletons that were born in the early stages of the Schumann-Rosen process because there is inflationary expansion in this phase and burst and growth proceeds at a singular fast rate. So we can do it as follows. So fix some integer n, some positive delta, and we will study the number of singletons born at after delta n, and that transformed it in doubletons within time nt after that burst. Then we'll get that this stochastic process converges to a time transformed version of a unit rate Poisson quantum process on the half-real line. And as a last example, again, we fix some positive delta to exclude this early born singletons. And by S, we denote the birth time of a singleton that was born at after delta n and transformed into doubleton in the shortest time among all such singletons. And also by T, we denote its lifetime. And the limit theorem here is that if we divide these values by n, then they converge in distribution to some two-dimensional random vector with an explicitly given density. And in this case, it's I'd say it's worth mentioning the outline of the proof that this limited random vector at first sight looks quite complex, but we can easily derive its density if we apply the Mecca equation to the expectation. If I take some Borel function g, write what the value of this function at these two random variables looks like as a sum, or the sum can also be a stochastic integral with respect to measure say 1. And then by applying the Mecca equation to the expectation of the sum, we can show that equals this integral, and from here we'd rather this f using exactly the density of its limited random vector. So that's all from me. Here's some useful references, and yeah, thank you for your attention, and be happy to answer to questions that are ready.
Okay, thank you very much for interesting talk, and maybe somebody have questions or comments, please.
Okay, that's me again. Thank you for an interesting presentation. I'm not sure I understood the first part, because it looks that you have a sort of infinite dimensional simplex. That's your this X space. Is it right? Or a simplicial complex, so because you have some faces of different dimension.
Yeah, we didn't thought of a proper infinite dimensional space, because we within this framework we can study the cycles of bounded lengths only. So in this case, our space is just union of this n-dimensional
It's
simplexes.
like a simplicial complex, yeah.
Okay, infinite dimensional simplicial complex. That's
Yeah.
the best description. Okay, that's clear. And another question: it is somewhere on slide 19, I think. You got some Poisson process, which is marginally Poisson, right? So you have some multivariate process which has Poisson margins.
Yeah, It was for example, this process where we count the number of singletons at time and t.
Exactly. So, do you know something about correlation of this thing? Because it looks like old work of Weinstein and Kreinin on Doops transformation of some flow of particles running through in homogeneous medium, and they try to compute some correlation structure.
I don't know about
yeah.
I don't know about this work to be honest, but from this explicit finite dimensional distributions form, we can as well get the two-dimensional distributions, and for example, correlation function of this process is not hard to derive from that.
Okay, but this formula doesn't tell anything about correlation structure. I do not think it will be easy to figure it out from this.
The explicit form of these dependence and distributions can be found in our work as well. So it will be in the form of some sums of independent Poisson random variables, and in case of r equals 2, it would be something like that there will be 3 independent Poisson random variables, and the x at time t1 would be the sum of, let's say, first and second, and at time t2 it would be the sum of third and second. So that.
Okay, thank you. I will have a look. Is it on the archive, this the work you are quoting on?
Yes, it's on the archive. I can send you the link in the chat after.
Okay, I made a screenshot. Thank you so much.
Okay, thank you. And maybe some other participants have some questions or comments, please. Okay, if there are no any other comments, then thank you again for interesting talk. And now it's your turn to have a talk on the Malarian calculus and applications, maybe next year. So please.
Okay.
Okay. We have to wait, I think, 3 minutes up to the next talk. Okay, Now it is time for the next talk. Speaker is Igor Chulakov from Institute of Mathematics, Academy of Science of Ukraine, with the talk Switching Problem on a Graph. Please, Igor.
Yes, greetings, everyone. I'm glad to present you our work with Andrey Yuryevich Pilipenko. Here we denote the graph as GM, and we denote for GM plus the positive part of the graph. In our work, we understand as a graph just the positive parts, non-negative parts of the coordinate axis in the space Rm. Let W be an n-dimensional Brownian motion such that starts from the positive part of the graph, and let Ck be a sequence of random vectors also from the positive part of the graph. Here you can see on the picture the graph in the space R3. Now let us build the process Xc on the graph in the following way. Let me draw it to you. So our process X starts on the positive part on the graph. Let's say on some axis I. It behaves like Wi, like a Brownian motion I on this axis up to the point when it first hits 0. Then, in this moment, we make a random jump Xc1. Let us imagine, for example, that this is a random jump Xc1, which pushes us up from 0, and in this moment we can switch on some another axis G, for example. After this jump, our process X starts behave like Brownian motion WG on the axis number G, and behaves in this way up to the moment when we hit 0 again. Then we make a random jump Xc2 that again pushes us from 0. It can push us again on the same xg, for example, and can push us, for example, in some another axis, and so on. So our process lives on axis like Brownian motion, and when we hit 0, we make a random jump that pushes us above and also can make us switch the axis. Now, let us consider the following 3 examples. First, when Ck are independent, identically distributed random vectors from the positive part of the graph, such that exists the expectation for each coordinate. The second one is when Ck are even non-random but cyclic sequence of vectors. And the last one when Ck is a Markov chain. For each of these examples, let us consider the sequence of the processes Xc divided by n. Build is the way that I described just right now, but this time we will multiplicate all jumps. We will divide all jumps by n. Now we are interested in the limit behavior of the process Xc divided by n, which we will from now denote by Xcn.
Excuse me, let me ask you about the case 2 and 3. I think that case 2 is partial case of 3. Yeah. We just have such Markov chain that from Xi1 we go to Xi2 and
yes, you're right. Yes.
Okay.
It's just the second one is more simple. We can prove it. We can prove our main result using some more simple mathematics.
I see. Okay, good.
So Now I wish to remind the definition of the Walsh-Brownian motion. It's a random process with the transition probabilities defined as you can see on the screen. And let me try to explain in very simple words how it behaves. It's almost the same process that I was drawing to you previously. This process lives again on the graph, and it behaves on the axis like a Brownian motion up to the point when we hit 0. And when we hit 0, the process can switch randomly to some another axis with on axis G with probability PG, and continues to behave on this axis like a Brownian motion. So you can see that it's really really looks similar for what I have described previously, but this time when we switch, when we are switching between axes, we make it in continuous way and we don't make jumps. So it would be natural to assume that when we will consider our sequences of processes, when we make our jumps smaller and smaller, it's natural to assume that the sequence of this process will tend exactly to the Walsh-Brownian motions. And the main result up to this time of our work is that the sequence xn tends to Walsh-Brownian motion with parameters pi, where you can see the formulas for pi in each of all these three cases. Talking in general and in simple words, in each of these cases, the pi is the relation of the heights and the number in average of our jumps on the axis number I to the sum of the jumps in average on all axes together. All these examples look similar. And now we will introduce the general approach to solve them, which resembles the Skorokhod reflection problem. It can be shown that all three sequences of processes defined previously can be given by the following formula. Later I will give for one of the examples the specific formulas for each of these functions. But now let's talk briefly. Here Wi, our Brownian motion from the beginning of the presentation. Function h is the function that contains information about jumps of our processes, and it is built from the vectors xk. And also we have functions ti and t tilde. It's some time functions. It means they are positive, non-decreasing, and they also cannot increase simultaneously. And these time functions regulate the behavior of our process. For some time, our process will behave like Wi, and for some moments of time, we will make jumps thanks to this term. Now I want to talk some words about Skorokhod theory. Anatoly Volodymyrovich Skorokhod formulated the reflection problem in 1961, and it proved to be an effective method for constructing reflected diffusions. The mapping associated with this problem turned out to be useful for solving various problems in QN theory. Skorokhod reflection problem has been generalized by different authors in many different ways. In particular, Andrey Pilipenko posed the problem of jump-like reflection and succeeding in constructing Brownian motion with jump-like reflection. But there are many other types of problems like Skorokhod. there are another generalization, for example, with shifted times, with time, with sticking, and so on. In our work, we construct a Skorokhod-like mapping that allows us to naturally glue together the positive parts of M dynamics on a graph. If we would be able to prove that this mapping is continuous with respect to functions w and h, then with this result we could obtain many limit theorems as a consequence of the continuous mapping theorem. And now I want to briefly introduce the general theory that was developed in our work. Now I want to give you the definition of the graph switching problem for the functions w and h that are non-random Kadlak functions, and the functions h are also non-negative and non-decreasing. So we say that the function x that lives on the graph is a solution to the graph switching problem for the basic function w and the compensating function h if for each I the function xi can be represented as follows, and this formula can be already familiar to you from our examples. And also we need some technical conditions. We need to have the sequence of numbers ak, bk, and we need that this sequence and the functions ti, t tilde satisfy the following technical conditions that you can see on the screen. They can look complicated, but let me try to explain briefly the intuition that stands for all these conditions. So in the definition of the graph switching problem, we have our starting functions, function w and function h, and we build the solution of the graph switching problem using these functions. Our process x, the solution, behaves for some time like function w, and for some time like function h. We call the function w the basic function. It is exactly the functions that we are trying to glue together on the graph. And we have the function h. It is our compensating function. Its purpose is to push up from zero our process x when it goes below zero. And also we have the functions ti, t tilde. It's time functions. What I mean when I say time function, it means they are positive, they are non-decreasing, and we don't want them to increase simultaneously. And these time functions regulates the behavior of our solution x. In some times our function x behaves like function w. For another time we behave like function h. There are moments of times when we behave like w, we denote for a, and we call it our basic regime. And another moments when we behave like h is called the compensating regime, and we denote it like b. Now we have the existence theorem which we can apply when we have the sequence of the solutions of the sequence of the graph switching problems for the functions wn, hn, and when we have some more technical conditions. First of all, we want that our sequence of functions w and hn converges locally uniformly to the function wh that is continuous. And let me try to explain briefly the second condition. It means just that we want this one this condition means that we don't want to see our solution xn goes to go far below 0 when n became bigger. And the second one means that we don't want to see that our solution xn goes far above 0 when we live in the compensating regime. Here, B stands exactly for compensating regime. And also we have another technical condition 3, and our theorem, existence theorem, says that when we have all these additional conditions, then the sequence xn is relatively weak compact, and any limit point of it can be represented in the following formula that reminds us the formula from the definition of the graph switching formula. In this formula, wi and hi are the limit function from the condition of the theorem. Here you can see them, w and h, and the functions ti, t tilde are the functions that satisfy the following system that you can see on the slide. And in this system, the functions li, here you can see again the same system. And in this system, function li is the running minimum of the wi. And now, thanks to the existence theorem, we can see the bridge that connects our theory that was developed to the Skorokhod reflection problem. Exactly. We can see that the formula of the limit point from the existence theory that have shown in the previous slide, this formula can be rewritten like this, thanks to the system from the existence theorem, where again Li is a running minimum of Wi. And now people who have worked with Skorokhod reflection problem can already notice that our limit function x, limit process x, is nothing else but the solution of the Skorokhod reflection problem for the function w, because we have the function plus its running minimum, and it is exactly the solution of the Skorokhod reflection problem. But except t, we have here some shifted time ti that is the solution of this system. Again, this is a system from our existence theorem. From the existence theorem, we know that the limit functions should satisfy the system that you have seen. If we know that this system has a unique solution, then it follows immediately that the sequence xn converges locally uniformly to x, where x is given by the same formula, and ti, t tilde are the solutions of the same system. But it is the question if that system 1 have a unique solution or not. And we have an answer to this question. We have a uniqueness theory. To introduce it to you, I need to give some technical definition of the level of constancy of the monotone function. You can see it on the screen. And here we can see the uniqueness theorem. So when we have some technical conditions that you can see on the screen, and I want to say that the first one and the last one have already been mentioned in the existence theorem. So actually we have just two completely new conditions that are expressed in terms of level of constancy. So when we have additionally these two conditions, additionally to the conditions of the existence theorem and the definition of graph switching problem, then we can claim that the system 2 is exactly the system from the existence theorem, has a unique solutions with respect to the functions ti and t tilde. And let me go a little bit back, and I want to explain you one more time why it is a very good result, why we should be happy when we have all the conditions of existence theorem and uniqueness theorem in the same time. So imagine that we have the sequence of the solutions of the graph switching problem that satisfies both the conditions of existence theorem and uniqueness theorem. Then the existence theorem tells us that there is always limit points for this sequence that represented by these formulas. So we have the limit points, but we don't know if that limit points are unique or not. But when we have also the conditions of the uniqueness theorem, we know that this system has the unique solution, and hence we know that this limit point of the sequence xn is unique. It's unique limit point, and in simple words, talking directly, we can just say that our sequence xn just converges to this x represented by these formulas, and its unique limit point. And now let me show briefly how we apply this theory to our examples that were introduced in the even beginning. So I remind you that now Xi, K are independent, identically distributed random vectors. Such exists the expectation for each coordinate. Here you can see the formula for that processes with jumps from the beginning of the presentation, and here you can see the explicit formula for each functions ti, t tilde, and h. Now with these formulas we can check directly that all conditions from the graph switching problem, from the definition of graph switching problems, are satisfied, and most of them checked just trivially because we build these functions ti, t tilde exactly to satisfy the definition of the graph switching problem. The only condition that is not trivial is the condition that that moments of time when we make switches have not limit points. It is just the consequence of some properties of Brownian motion that it has independent increments, and when it hits zero, it behaves. It continues to behave like we have some new independent Brownian motion. Now we can also check that introduced earlier functions h, I, n converges to the function t multiplied by expectation of xi, and convergence in in terms of almost sure, converges almost sure, and local uniform with probability 1. And now with these conversions, it can be easily checked that also all conditions from the definition of the graph switching problem, existence theorem and uniqueness theorem are satisfied almost surely the same time. And now it follows immediately from our theory that almost surely the sequence of processes xn converges to function x that can be represented in this way, where functions ti, t tilde as a unique solution of the following system. And now what remains is just to solve this system. And now I want to use some results from the last article that was published in 2025, the article of Bayraktar. We have theorem that tells us when we have Brownian motion in Rm that starts from the positive part of the graph, and we also have some numbers, positive numbers pi, such that also the sum of pi is equal to 1. We here denote again Li as the running minimum of Wi, and suppose that the functions ti, t tilde are solutions of the following system, then the theorem of Bayraktar's tells us that the process X is the Walsh-Brownian motion with the parameters pi. And going back to the previous slide, we can see that we established that our process X can be represented exactly in the same way. Here you can see it, but except constants pi, we have here expectations of Xi, and we have the same system. So now we are exactly in the conditions of the theorem of Bayraktar, except maybe that we don't have the conditions that sum of Xi is equal to 1, but we can to deal with this very simply just by dividing here by the sum of expectations and multiplicating it back here to change nothing. And now we are exactly in the conditions of the theorem of Bayraktar. And using our general theory and this result, we can claim, I remind you our main result, that the process Xn converges to Walsh-Brownian motion. And I also want to note that another two cases with non-random jumps and Markov chain are solved almost the same. We will have exactly the same system that looks exactly. Sorry.
Igor, you have 2 minutes to the end of the talk.
Yes. Sorry. Yes. Thank you for attention. We'll be glad to hear your questions.
Okay, we have just time for one small comment or question, please.
Well, the shortest comment is that another name for this is Brownian spider.
Yes.
Okay. Okay, then thank you very much for your talk, and we have just 1 minute for the next talk. Okay. Our next speaker is Sadillo Sharipov from Romanovskiy Institute of Mathematics, Uzbekistan Academy of Science. Please, Sadillo.
Yes, thank you very much. First of all, it's a great pleasure for me to participate in this conference dedicated to Anatoly Vladimirovich Skorokhod. I want to say some words about Skorokhod since I am a young mathematician. Skorokhod, basically, I think Skorokod's works made a revolution in probability theory, and as he co-authored a seminal treatise on stochastic processes with Gehman, praised for its rigorous yet accessible approach. And I think his key contributions include the Skorokhod topology, where he proposed four different topology in the Skorokhod space, and it's well known the Skorokhod integral and the Skorokhod embedding theorem, which have become cornerstones in the study of random processes. And it's well known the Skorokhod problem, which addresses Skorokhod stochastic differential equations with reflecting boundary conditions, also bears his name. And I found information about his scientific works. He had 450 scientific works, papers, including more than 40 monographs. And I think he's a prominent mathematician in the 20th century. Thank you very much. And my talk is about some branching processes, and the theme of my talk is asymptotic results for branching processes with immigration. And so I want to tell some my results on this direction in this field. First of all, I want to consider branching processes with immigration in the first of my outline, and the second, I want to briefly consider partially observed branching processes with immigration. So I start. So description of the model. We have some probability space, and this space we are given two sequences of independent and identically distributed random variables. So the first CKA is an array of IID random variables with non-negative integer valued random variables, and the second epsilon k, this is a sequence of non-negative integer valued random variables. We shall assume that these two sequences are independent from each other. And the branching process with immigrations is the following process, which is defined by this formula. This is epsilon k. When the epsilon k does not participate in this formula, we came to the well-known processes, which is named as Galton-Watson process with Galton-Walton processes. Yes, and this process. This is Markov chain. It is not difficult to check this process is Markov chain, but in the case when epsilon k is dependent, but however this process is no longer Markov chain. So we denote by A this mean of this random variables is finite, and according on the values of this A, we have the following definition. This process, the branching process of immigration, is said to be subcritical, critical, and supercritical if this equation and inequality holds, respectively. I consider here some unlike the classical case, I consider here when the epsilon k is non necessarily identical distributed. So in the language of branching processes, this epsilon K is interpreted as the immigration sequences, and we consider, we suppose that the mean of the immigration and the variance are finite, and we denote them by alpha n and beta n respectively. And we assume that these two variables are uh, are are of this form. So, and in this case, the mean and the variance of this process are can be calculated by this formula. And here you can see the sigma squared n is equal to this one, to this formula. And as soon
I
as
have a question. So epsilon may be dependent,
yes,
and psi, is there any dependence between psi and epsilon?
Xi and epsilon, I consider no. I said that here 2 seconds are independent from each other.
Okay.
If there is condition is violated, I don't know any.
Yeah, I understand. So they're independent, but epsilon k may be dependent.
Yes.
Thanks.
And here covariance appears, and then so I want to say that here that the variance of this process equals to the sum of the delta squared and sigma squared n, and we must consider some conditions under which some conditions which ensures that the which terms are dominated each other. And in the following I will consider these cases, and we need some Lindbergh numerical characteristics for the immigration processes and we define processes by this formula, and this formula and the z and t is it's not difficult to know that this process is the trajectory of this process is lies in the Skorokhod space D infinity, and the following result was obtained by Rahimov when he considered the critical case with when the immigration variance is finite, and if these conditions holds, then this processes weakly converge in Skorokhod topology to the limiting process ZT, where ZT is defined as follows. And here, if, for example, beta n is O small n multiplied by alpha n, then we have this limiting process, and I didn't say that this WT is a standard Wiener process. So we have time changed Wiener process in the limiting process in the limit. Yes. Yes, it's very interesting result, because in the theory of branching processes we didn't see a Wiener process in the limit, and because in these conditions, the beta alpha, the three conditions ensures us to get these limits. So now I want to generalize this Rahimov result to the dependent immigration case. So as a dependence, I consider the following dependence. So I have sequence epsilon k. This sequence, I assume that this sequence is defined on this probability space, and I define here sigma algebra generated by this sequence, and consider two sigma algebras in this F in the sigma algebra, and we consider this rho beta R mixing mixing between two sigma algebras. This is it's clear it's finite because one can estimate covariance by Cauchy-Schwarz inequality by the squared by variance of these two random variables, and we define the row mixing coefficients between for the sequence of random variables by this inequality, and we give definition. A sequence epsilon k is said to be a row mixing if this sequence goes to infinity, goes to 0 as k goes to infinity. So this mixing condition was introduced by Kolmogorov and Rozanov in 1960. I want to generalize Rahim's result, and I consider only the first case. So I only consider critical case here with finite offspring variance, and I assume that migration sequence is row mixing with this rate, and if these two relations hold, then we have weakly convergence in Skorokhod space D, where WT is the standard Wiener process. Then I want to consider nearly critical branching process with immigration. So for what is this process? So, and here there is a double index, and we consider branching process in scheme series, and we suppose that the epsilon k I and is an array of IID with non-negative integer valued random variables with this finite mean and this finite variance, and here I suppose that epsilon k n are non-identical distributed with finite mean and this finite variance. Consider the equation of the branching process with immigration, and we denote its mean and variance by alpha n k and beta n squared k. And so one can calculate its mean and variance of this process. And I here provide a definition. This family is said to be nearly critical if alpha n goes to 1 as n goes to infinity. And I have this following definition. A triangular array of random variables is said to be an array of row-wise row mixing random variables if for every n the sequence is a row mixing sequence of random variables. So in other words, in each array you have a row mixing. As I consider an array, so my row mixing depends on array, on n, and so I denote by row n dota is b. This is the mixing coefficient of the sequence for any n. Here I have to consider the following assumptions to provide the results, and these conditions are involved in papers by Rahimov when he proved deterministic approximation and fluctuation type results for branching process with immigration. And here I provide one of the theorem which extends Rahim's results from independence to row dependence, row mixing condition. So we assume that the immigration sequence are array of row-wise row mixing random variables satisfies this condition, and if the following C1 and C4 condition holds, then we have deterministic approximation where in the Skorokhod space D, where the limiting process is calculated by is equal to this one, and we have convergence to the deterministic function. And the following results was obtained by Rahimov. Together we obtained the following result, and it's very interesting that if we assume that immigration sequence are all arbitrary dependent without any conditions of dependence, is arbitrary dependence then, and if conditions C1 and C3 hold, but look here I have to put these conditions Bn is O squared alpha squared n, then we have this convergence. In the independent case, Rahimov proved this theorem only for the case when the beta n is O small n multiplied by alpha squared by n. So we remove this n, and this helps us to consider arbitrary dependent random variables of immigration sequence. In the next, I consider fluctuation limit theorem for nearly critical branching process with immigration, and I provide a definition, the definition of m-dependent random variables. So a sequence of random variables epsilon k is m-dependent if the two random vectors are independent for all g. For example, when m equals to 0, we have we arrive at the definition of independence of random variables. So as I consider null critical branching processes. So I here the sequence, an array of random variables C chi n is said to be row-wise m-dependent if for every n this sequence is m-dependent. So in each arrow we have m-dependence, and we assume that this m-dependence depends on the row index, and it goes to infinity with some rate. So this rate here in the condition C5 it's I write this in which rate must be m tends to infinity. Yes, here in the independent case, this m doesn't participate in this formula. It can be removed from this formula m. But in the dependent case, m dependence, this here one must to put this condition. Under this condition, so I'm sorry. So I provide the following theorem. Let's for each n immigration sequence is a sequence of m-dependent random variables, and we assume that C1 and C3 and C5 conditions hold, and for every epsilon bigger than 0, the Lindeberg condition holds for immigration sequence. Then we convergence Z and T. We could converge in Skorokhod topology D to this limiting process, to the time changed Wiener process, where time changed is defined as this formula. Here WT is the standard Brownian motion. So now I have no time, but I have time, so I can continue my talk. So I consider here partial order branching process with immigration. We have a discrete time, and we start with 0, and we assume that x no infected individuals in an infinite we have x0 number infected individuals in an infinite population, and we made some observation. And observation in the following manner we do. Each infected is detected with probability theta and undetected with 1 minus theta, where theta is unknown, but it's a number which is bigger than 0, but it may be maybe equal to 1. And we can assume that Z0 number is detected and U0 is undetected individuals, and we have some spread. Spread this means that undetected in fact according to probability distribution theta, and detected are isolated between times and n plus 1. And so in fact according to the same to the probability distribution, this is zeta thing. So then we have some iteration. We have x1, and this is equals to new infections from z0 and u0, and this process repeats infinitely. And this model has a key feature that the observation impacts the process, and this means that this reduces the spread. This model is named as partial observed branching processes. If we have any, for example, if here theta equals to 1, so we have no any observation. So in mathematics we can provide this mathematically we can we can explain this what I said here. So we have a sequence Xi and I. This is a family of IID Bernoulli random variables with probability of success theta, and two sequence Xi and IG, where G equals to 1 and 2. This is two independent families of IID random variables taking non-negative integer values, and these two sequences may follow different probability distribution, so they are maybe equidistributed from each other. Yes, and these three sequences are independent from each other, and we put so this is a offspring distribution. Yes, it's equal to undetected plus detected random variables. So if we substitute in the definition of the branching process with immigration, we have the following equation, and the partially observed branching process with immigration is defined as follows. For example, as I said, if theta equals to 1, we have no if we have no observation, we came to the definition of branching processes with immigration. Now here we define the process. We define process, and here I provide the following theorem. I consider here only critical case, and the offspring variance is finite if alpha tends to infinity, such that beta n is O0, small o, and n multiplied by alpha squared n. Then we have this convergence in Skorokhod topology, where the limiting processes is a deterministic function. So I said if we have no observation, this means that theta equals to 1. This results coincide with the well-known results by Rahimov. And now I consider stationary immigration. This means that number of immigration duels are identically distributed, and I'm sorry, here it must be independent and identically distributed, not stationary. Identical distribution it's a good formulation, and we consider the random processes, and provide the following theorem. In the critical case, with the offspring variance is finite, and here mean of the migration is lambda, it's finite also, and the variance of the migration is also finite. Then we have this weak convergence in Skorokhod topology, where the limiting process here is a diffusion process, which starts with zero at zero, and the generator of this diffusion process defines as follows. Here, f a function which belongs to the space of infinitely differential functions on this set, and the set has compact supports. This result, when theta equals 1, generalizes, extends wave unique result, which was published in 1979. So I finished. If you have any question, I am ready to. I shall try to reply to your questions. Thank you.
Okay, thank you for your talk.
Yeah.
Maybe somebody have questions or comments, please. Please. Okay, I have a question relatively to your last slide. Can you show it again? Okay, this one. As far as I understood, you have such like diffusion process with linear coefficients, yes?
Yes.
This is a stochastic exponent, I think, yeah? Something like
Yes.
stochastic exponent, yeah?
Yes.
I see, okay. You even can say something about its limiting behavior.
Yes. So the method of the proving these results is based on the Martingale limit theorem, or based on functional limit theorem for Martingale difference. So you need to check three conditions of three conditions for obtain the limiting process, and here this theorem is maybe
No,
found
I mean that you can say that this diffusion has the precisely described behavior at infinity.
Andrey Anatolyevich, this process is not linear diffusion. This is squared Bessel process.
You have this square root, okay. While then again we understand this limiting behavior, yes? Why not?
Sure.
This generator can be written
Okay.
as a stochastic differential equation. Yes.
Yeah. From this conclusion, nevertheless, yes, I missed this that you have square root in diffusion. Then. Of course, you can say a lot about the limiting behavior, about the behavior of this process. Can you make some conclusion about your processes yn from this?
Conclusion about yn.
Yes, about the limiting asymptotic behavior when t tends to infinity, about the behavior of the processes yn.
So I think that what here the limiting process is yt is function analog of gamma distribution, because if I fixed it 1, so I must came to the Senator theorem, which states that this normal sequence, normal process, normal sequence weakly converge to gamma distribution. So this it must be like this. YT is a functional analog of the gamma distribution.
Okay, okay. Thank you.
Thank you.
Thank you for your
Thank you.
talk. And actually, we have to switch to the next talk. Thank you very much.
Thank you very much. Thank you.
Okay. And now we have next speaker. Next speaker is Vadym Tkachenko from Institute of Mathematics of National Academy of Science of Ukraine, from our department of the theory of stochastic processes, with the talk explosion and implosion of semi-Markov Beer-Diaz processes. Please, Vadym.
Hello, can you hear me well?
Yes.
Okay. Thank you very much for the invitation. And this is a joint work with Andrey Yurievich Pilipenko. You can see the name of the topic on your screen, and let's begin. Consider first a birth-death Markov chain xk on natural numbers with 0. So at each state, we either go right or left with probabilities p and q. And we have a reflection from 0 with probability 1. Such models are used, for example, to model some populations. And these assumptions turn out to be very non-restrictive. And I shall note that here all probabilities p and q are non-zero and add up to 1. So next, we want to construct a process, a continuous time process, that has the same transitions on the state space as our Markov chain xk, but spends some random time at each state before making a jump. So, for example, we could start at 1, wait some random time tau 1, then go right, wait tau 2, go back to the state 1. But here we have a problem, because now our process will be dependent of its past. So there is a way to overcome this, and let's define our process. Let tau I be a sequence of positive random variables. And for each tau I, consider a sequence of its copies, of its independent copies, tau ik. And suppose all these sequences and the Markov chain xk are independent of each other. Now let's make 0 our first moment of time and define random moments of jumps recurrently. So in order to define the next moment of jump, we take the previous one and add the independent version, independent copy of the waiting time, which is defined by the position of our Markov chain xk. Now, our first definition, the process x of t, which is just the value of our Markov chain on the interval between 2 consecutive jumps. So this process is called semi-Markov process with the embedded Markov chain xk and waiting times tau I. Such processes are also called continuous time random walk. Okay, now we need to introduce some new concepts. And the first concept is explosion. Denote by sigma n the first moment when our process x hits some state n. For example, let's consider sigma 2. So this is the first moment when x hits 2. And for example, we could start at 0. Then we wait this tau 0, its independent copy. For example, we go to 1, wait tau 1, we can go back, and we sum up all the waiting times, and then we can jump to the state 2, and we stop the summation. Now we can introduce this variable sigma infinity, and it will represent the moment of hitting infinity. So what's the deal? In some cases, you see that the possibilities of our trajectories become larger and larger. And we can spend a lot of time reaching some high level. But if these waiting times are small enough in some sense, still we can reach arbitrarily large point. So to make it more real, our population, for example, of some bacteria can grow rapidly, even exponentially, in a finite time. Well, of course, it cannot be infinite in the real world, but it can become extremely large in a small amount of time. So our definition for this is the following. We say that X explodes to infinity if this moment of explosion is finite. And we want to find necessary and sufficient analytical conditions for explosion. So we want some conditions in terms of the parameters of our process. I mean the transition probabilities and waiting times. One more concept, and it is called implosion. I will begin with a picture. So suppose y 1, 2, and 3 are independent.
I'm sorry, you mean sigma infinity is finite almost surely?
Well, yeah, we can say that, or we can define it for each omega. Yeah, but it's fair point. Thank you. Okay. So let's introduce the concept of implosion. Suppose y1, 2, and 3 are independent semi-Markov processes as defined above. And suppose that y1 starts at 1, and we wait until it hits 0. Well, actually, the trajectories of our process would be like stairs, yeah? So piecewise constant. But for a better image, I will draw them in this fashion. So our y1 starts at 1, and at random moment theta 1, it hits 0. Then suppose y2 starts from 2, and we wait until it hits 1. So y3 starts from 3 and goes to 2. And now using two different scenarios. If we continue doing this procedure, it may happen that this total waiting time until the hitting of 0, it can grow indefinitely, or it can be finite. And in case when it's finite, what will it mean? It will mean that our process started from a very high place, from a very high state, and reached 0 in a finite time. And we call it the implosion. And it's closely related to the notion of entrance points or entrance boundaries. So our process can be started from its boundary at infinity. And it will, so there's a rigorous way to define the process that starts at infinity. So we take the sequence of independent copies of our process, start them at n, define the stopping times, and now we need to sum the respective waiting times of the individual processes. So like this. And our definition that the process implodes from infinity if this variable at infinity is finite. Of course, yeah, it will be better to maybe say almost surely, or we still don't know that this event happens with probability 1. Yeah. What if it happened with probability 1.5? Yeah. So it's better to introduce this notion for each omega, and then we will see that indeed the probability of such events is either right. So these are transition probabilities. And nu I is defined in terms of transition probabilities and the waiting times. This delta k is closely related to the notion of a scale function, and this nu I is related to the notion of the measure of speed. So our theorem 1, for every initial distribution of x, we have the following alternative. So the process x, our semi-Markov birth-death process, explodes with probability 1 if and only if the following two series converges. And note that here we have the partial sum of this series, so from 1 to k. And we have this second shadow part, so vice versa. It explodes with probability 0 if this series diverges. And the next result is the implosion criterion. Once again, we have the same notation. And we have that the process x implodes with probability 1 if and only if the following two series converges, where now we have not the partial sum, but the tail of our series. And also additional condition, the series of delta k is infinite. So this delta k tells us about the following. It tells us about is the boundary reachable or not. So here it means that our boundary is not reachable, so we can't access it from our phase space. And this expression here tells us about how much time will we spend in sort of in the region of our boundary. Okay. And I want to draw now some connections and comparisons with the known results for one-dimensional diffusions. And I hope this series will make more sense, become more meaningful. So assume that X is a one-dimensional diffusion with the scale function S and the speed measure M. So S and M are some real strictly increasing functions, and S is continuous. Then the boundary is attainable, so we can reach it in a finite time with positive probability, if and only if the following integral of the measure of speed over the scale converges. So here you can see the definition of this expression under the integral. And it does not actually depend on this starting point x1, x0. And attainability of the boundary point plus infinity is actually equivalent to explosion in our setting. And this condition 1 from one-dimensional diffusions is analogous to our explosion condition. So here you can see it once again. And we only need to replace the integrals by discrete sums and define the scale and the speed measure as follows. Here you can see the delta k's and the new i's. So we got the conditions that are analogous to the classical results for diffusions. And for the case of implosion, here, as I already mentioned, we need to talk about the entrance point. Yeah, so we cannot reach it, but we can start from this point and continue to the case. And in terms of the scale and the speed measure of diffusion, plus infinity is the entrance point if and only if the following integral is finite and the scale is infinite. And of course, if we once again denote Sn and Mn as previously, we get that our implosion condition is identical, analogous to the condition for one-dimensional diffusions. Okay, and yeah, I would like to add some historical notes here. So as far as I'm concerned, it all began with works of Feller, who studied diffusions, and this classification of points is due to him. So we have regular, natural, entrance points. Then this work was continued by Ito, and then many others. For example, okay, I think I will go further now. Yes, and I will continue about history on this slide for a little. So now let's see what our conditions, what are our two criteria will give in some specific examples. And the first example is the case of the Markov process. So here we suppose that our waiting times, tau I, are exponentially distributed with some parameters ai. This is true if and only if our process is Markov process. And then we can explicitly calculate the Laplace transforms and get that our explosion conditions becomes the following. And this condition is a classical one. It can be found in the book of Dynkin and Yushkevich, where they study Markov processes and establish this criteria. Actually, the ideas from this work are very crucial to this one. Okay, and this expression looks rather difficult, but we can consider a homogeneous process. So now all the transition probabilities are constant. And now this really simplifies, and our explosion condition is the following. So P must be greater than Q. This means that our process tends to go right. And the following series should converge. To obtain these results, it was crucial to use the Markov property and the strong Markov property of the process. But it is very interesting that our approach allows to do this. So suppose now the waiting times tau I are distributed as tau over some ai, where ai are some positive numbers, and tau is a positive random variable such that it has a finite expectation. Then it's not difficult to show, using the asymptotics of the Laplace transform, in this case, that we have the same explosion condition for a non-Markov process. Yes, and it's very interesting. It's the first extension of that our results give. And for the next part, consider the implosion condition. Once again, it looks very similar, but now it is the condition for implosion. In the homogeneous case, we actually have two conditions. So one is pretty straightforward. Yes, so our process now tends to go left. Yes, we want to have the following picture. So our process starting at plus infinity can escape and continue living in the phase space. But then we have this interesting case. Actually, we can have asymmetric random walk. And the condition of implosion changes as follows. So AI should go to infinity faster. So our average time should be smaller in this case, which is pretty intuitive. Next, this is will be a new result. Suppose that our waiting times, tau I, once again, are tau over some AI, and the limit of AI is infinity. And we suppose that tau has distribution function f. And now suppose that 1 minus f varies regularly at infinity with exponent minus alpha, where alpha is between 0 and 1. This means that the function 1 minus f is x to the minus alpha times some function L, where L is a slowly varying function at infinity. For example, a logarithm. And now the explosion condition can be written in terms of the tail of this distribution function f, as you can see here. And the explosion condition looks similar. Okay, and one important special case of the previous example. So when our waiting times were had regularly varying tails, is the case when this tau is a positive random variable with alpha stable distribution, where alpha is between 0 and 1. Then the Laplace transform for this distribution is known, and we can calculate the Laplace transform of our waiting times. And the explosion condition becomes the following. So it looks like the one from the Markov case, but now we have this power alpha here. And the explosion condition looks analogous. Okay, so this is the last example, and I have a couple of minutes, so I wanted to briefly go back to the Markov case and try to give an idea of the proof. So it's interesting how do we get this two series? And the answer is actually in the Markov case. So in the Markov case, we have the following. So if we consider our state space, some state I and some interval from M to N, and we want to study how much time in average will it take for our process to exit this interval. And it turns out that we can write a very simple equation for this value. And this is what Dynkin and Nishkevich did. They solve this system explicitly and get these double series. And now the interesting part is that in the semi-Markov case, our waiting times may not have expectation. So we cannot use this technique directly, but we can try to use the Laplace transform instead, because it is defined for all positive random variables. And now we were able to write these equations similar to the ones in the Markov case, and estimate their solutions by solution which has a similar formula to this. Okay, so that's how we managed to find these conditions. So I think this is all for me. Only a few words about the references. So this is the book I was mentioning, a book by Dynkin and Yushkevich. And the results about one-dimensional diffusions can be found in the book of Ito and Carlin and Taylor. So Ito actually had a big impact on this field of study. Thank you for your attention. This is all from me.
Okay, thank you very much. Maybe somebody have questions or comments. We have 2 minutes.
Actually, maybe I have two short questions. First of all, I think that in your setting, it is also possible to write down all characteristics of the time of explosion. First of all, expectation. I suspect that expectation is just the left-hand side of your criterion, this double sum. But maybe it is possible for variance or some more general characteristic. Yeah?
So you mean to write the expectation of the moment of explosion?
Yeah, I think that there is no problems with expectation, but maybe some another also some another characteristics.
But in some cases, the expectation may be just infinite. Yes.
Yeah, if it is finite, of course.
Okay, it's interesting.
Yeah, and the second question may be quite strange. What do you think? Maybe there is some mapping between some natural coupling, so some mapping of one semi-Markov process and some another semi-Markov process, maybe by some reversal of axis or scaling, which maps explosion effect to implosion. Is it possible or not?
It seems. I think it seems natural, right? So it looks like some kind of reflection.
Yeah, exactly.
Reflection. Yeah. Yeah, it's very interesting. I need to think about the way to do this. By the way, talking about some mappings, it is also quite easy to compactify our space and to make it finite. And then we will have like, we can talk about convergence of our processes to some process in Skorokhod topology. So.
Okay, thank you.
Okay, we have no time for question, unfortunately, because we already have time to for the next speaker. So maybe in private discussion. And we have a next speaker, Valeriya Kotelnikova from Taras Shevchenko National University of Kyiv, with the talk allow the iterated logarithm for small counts in the infinite bone boxes scheme. Please, Valeriya.
Thank you for introduction and hello everyone. Okay, I hope everyone can see my slides and it's okay. I'll be talking today about the results we obtained recently with my advisor, Sasha Iksanov, where we proved a law of the iterated logarithm for small counts in the infinite balls and boxes scheme. But before stating the results itself, I will define first what is infinite balls and boxes scheme and what do we call their small counts. Then I also discuss the most common approach, how to prove any sort of limit theorems for small counts in the scheme. And also I will discuss how this problem is connected to another law of the iterated logarithm, which we proved 2 years ago, together with Sasha Iksanov and our Polish colleague Darek Buraczewski. So let's start. And we start from the definition of infinite balls in boxes scheme. It is also called infinite occupancy scheme, Carlin's occupancy scheme, or any other combination of those words. But in essence, it is the same. So it is defined in the following way. There is an infinite array of boxes, numbered 1, 2, 3, and so on, and balls are distributed independently over those boxes with probability pk of hitting box k. Here, pk is a discrete probability distribution. And additionally, we assume that there are infinitely many positive pk's. In a language of balls and boxes, it means that with positive probability, a ball may hit one of infinitely many boxes. And let's look at one of possible realizations of this scheme. So at time 1, we grab the first ball and it falls into some box, let it be 100. It happens with probability p100. Then at time 2, you take the second ball. It may fall, for example, into the box number 2. It happens with probability p2. And it is important that where the second ball falls does not depend on the outcome of where the first ball fell. And we continue this process indefinitely. And so far we just defined the distribution process itself, but we didn't define any numerical quantity for which we may prove the limit theorem. So let's do it. One of the most important characteristics of this scheme are the following. First is the number of boxes containing at least j balls, which we denote by kj, and n in parentheses here stands for the total number of balls which were distributed. In particular, if we consider j equals 1, we need to count how many boxes contain at least one ball, which in human language means that we just want to count how many boxes are occupied. And another characteristic we're interested in is the number of boxes containing exactly j balls, which we denote with the star. And the difference between first characteristic and the second is in words at least or exactly. This second characteristic with the star is called small counts, so our goal today is to state laws of the iterated logarithm for small counts. Let's count those characteristics for this particular realization so we get a better feeling what they mean. First, we write everywhere in parentheses 5, because so far we managed to distribute only 5 balls. The number of occupied boxes here is 3. The number of boxes containing exactly one ball is 1. It is box number 3. The number of boxes containing at least and exactly 2 balls is the same, it is 2, so sub-boxes 2 and 100, and all other characteristics are 0, because we do not have any boxes which have at least 3 or exactly 3 or more balls. And there is one crucial difference between the first characteristic and the second, even though they may seem to be very similar. The first characteristic is not decreasing in the number of balls n. Indeed, if at some time n, a box had at least j balls, then at later times it will not lose the property that it has at least j balls, so it is not decreasing. However, small counts are not monotonic at all, because if at some time n we had a box which had exactly j balls, then this box may lose this property at later time if the new ball arrives. Okay, there are only few limit theorems which may be proved for the scheme for general discrete probability distribution pk. In fact, we are aware only about one of them. It is the strong law of large numbers for the first monotonic characteristic, so the number of boxes containing at least j balls. However, if you want to prove the strong law of large numbers for small counts, it does not hold anymore, and there can be constructed a counterexample. And the reason for it is because the small counts are not monotonic in the number of balls n. Therefore, we still want to prove some limit theorems, so we need to impose some additional assumptions on discrete probability distribution pk, but we want those assumptions to be not too restrictive, so that still the most common distributions which come to your mind satisfy those imposed assumptions. And the most convenient way to state this assumption historically is to state it in terms of a counting function of sequence 1 over pk, which we denote by rho. So it is the number of such indices k that 1 over pk doesn't exceed x. And the common assumption on the counting function is that it is regularly varying at infinity of index alpha. In other words, it means that at infinity it behaves like x to some power alpha times some slowly varying at infinity function L. And if you've never seen slowly varying functions, you just may think of this as constant or logarithm or 1 over iterated logarithm or something of this style. So this assumption was suggested first in 1967 by Carlin in his seminal paper, where he was the first one to suggest this assumption, and then he was able to prove central limit theorems, in particular for small counts, in his paper with the help of this assumption. And that's why also the scheme is called after him sometimes, Carlin's occupancy scheme. Let's also discuss why we require alpha to be exactly from 0 to 1 and not anything else. So to do that, let's look at the behavior of the counting function when x tends to the infinity. We need to count how many indices k are there that 1 over pk doesn't exceed a number which goes to infinity. Then the number of those indices itself diverges to infinity, and this is where we have the first restriction from that alpha should be at least 0. On the other hand, you may simply prove from some easy tools from analysis that even though counting function diverges to infinity, it does it not faster than just x. Therefore, we obtain the second restriction that alpha cannot exceed 1. And it turns out that this infinite occupancy scheme has different behaviors when alpha is 0, when alpha is 1, and when alpha is the rest, so from open interval from 0 to 1. And in particular, the loss of the iterated logarithm, which I will state today in the end, also confirms this difference of behavior. Okay, so we know which assumptions we can impose, but still, how to approach all of those quantities. I will do now some little calculations for the number of occupied boxes because it's the simplest quantity to discuss, but we may do exactly the same for small counts. So the first thing which comes to mind is to represent the number of occupied boxes as the sum of indicators that k's box is occupied. And with this at hand, we may easily count the mean of the number of occupied boxes. To do that, we just need to count the probability of those events. However, if we want to count the variance or any other moment or even exponential moment, we ask ourselves, are those indicators independent? Because if they are, our hands are untied and we are free to count more or less in easy way all of moments, including exponentials. But unfortunately, it is not so. It is not true. So those indicators are not independent, and to see that, let's consider not exactly those events, but the opposite events, so that the boxes are empty. The probability that a k's box is empty is the following. So you want a ball to fall anywhere except of box k. So you are happy with any event except of the one which happens with probability pk. And you want it to repeat for each out of n balls. So this is how we get the final expression. Similarly, we can calculate the probability that two distinct boxes k1 and k2 are empty after n balls were distributed. So we are good when this ball falls anywhere except of box k1 and box k2, and we want this to hold for each of n balls. And we can see that it does not equal to the product of separate probabilities for box k1 and box k2. So there is no independence, and even while counting variance, we will have like this double summation, which is very unpleasant to work with. But we still want those indicators to be independent. And fortunately, there is a way how to do it. It is to perform so-called Poissonization procedure. So in short, what we will do is we will change the time scale when we throw the balls. And then miraculously, by the properties of Poisson processes, it will turn out that in the Poissonized version, those quantities will be indeed sums of independent indicators. So let's look now in more details what is going on. Let's denote by pi a Poisson process on the negative half-line of unit intensity, and by S1, S2, and so on, its arrival times. So pi simply counts how many arrival times you observed up to time t. Also, you may think of those arrival times as a random walk with a step which has exponential distribution with unit mean. So to recall, in the deterministic version, we were throwing the nth ball at time n. So if we introduce the continuous time scale, at time t, in total in all boxes, there were integer part of t balls. In the Poissonized version, we suggest to change the time when the nth ball is thrown. So instead of it being n, let it be Sn, which is the nth arrival time of Poisson process. So then, at time t in total, we will have now pi of t balls, because it is exactly what Poisson process counts. Why does it help? Let's denote by pi k the number of balls which fell into the box number k in the Poissonized version. Then the total number of balls, pi of t, is the sum of numbers of balls in distinct boxes k. By the thinning property of Poisson process, those sub-processes pi1, pi2, and so on are independent Poisson processes of intensities p1, p2, and so on. The key word here is independent. Because with this at hand, we may represent the Poissonized version of small counts as the sum of indicators that the number of balls in the box k is equal to j. And since those sub-processes pi k are independent, those indicators are also independent. And it is exactly what we wanted. And we can do the same for this monotonic characteristic as well. We just need to change equals to j to inequality that it's at least j. And later, to distinguish the Poissonized version and deterministic version, we just need to look which letter is written in the brackets. So if we have letter t, it means we consider the Poissonized version of the process. If it is letter n, it means we are talking about the deterministic version of the process. And this explains the common procedure which is taken when we want to prove a general limits, any limit theorem for those two characteristics, small counts or the number of boxes containing at least j balls. So first the scheme is Poissonized, then the problem is solved for the Poissonized scheme, and last step you need to do depoissonization, which means that you need to come back from the Poissonized scheme to the deterministic scheme, which was your original problem. And usually step 2 is the hardest, because for depersonalization there are some usual tricks which work mostly in every setting. So that's why today I will concentrate only on how to solve problem for the Poissonized scheme, which means how to prove the law of the iterated logarithm for the Poissonized version of small counts. And since the Poissonized version of small counts is infinite sum of independent indicators, we may think about it as a part of a general problem when we want to prove a law of the iterated logarithm for some general infinite sum of independent indicators. And this is a problem which we actually considered 2 years ago with Sasha Eksanov and our Polish colleague Darek Borachevsky. So let me introduce you a little bit into what we did 2 years ago. Let's denote by A1, A2, and so on, independent families of events which live on a common probability space. And we are interested in process X, which, as promised, is the sum of indicators of events AK, which are independent events. So the prerequisite on X, which we want to hold, is the following. First, we want the process at each fixed time t to be almost surely finite. And then, moreover, we want the mean of this process at each given time t to be finite as well. Then we also obtain for free that the variance of this process, since it does not exceed the mean, it is also finite. Why do we want all of this to hold? Because we expect in the law of the iterated logarithm the centering to be the mean of the process and the normalization to be a function of the variance. So we want all of those quantities to be finite for given t. And also let's mark that we denote by b the mean of the process and by a the variance, because we are going to use this notation later. So to prove a law of the iterated logarithm, of course, we need some further assumptions. And the first which comes to mind that we require the variance to diverge to infinity, because if this does not hold, then even the central limit theorem doesn't hold, let alone the law of the iterated logarithm. The second assumption, which we imposed 2 years ago, is the following. So for s smaller than t, we assume that the set of events ak of s is included in the set of events ak of t, which in intuitive language you can think as the following, that the family of events ak is non-decreasing in time t. And we also assume some other technical assumptions, but it is the point when we can stop, because for our applications, for small counts, events ak are events when those Poisson subprocesses are equal to j, and for the number of boxes containing at least j balls, those are events that Poisson processes are at least j. For the second process, this assumption A2 indeed holds, because if at some time s there were at least j balls in a box, then at later time t, those j balls in a box will not disappear anywhere. However, for small counts, which is our target today, this assumption does not hold, because even if at some time s we had j balls in this box, it does not guarantee that later the amount of balls will stay the same. It may increase. That's why we see that this assumption A2 does not hold, and we need to do something about it. So we tried to modify the proof of the law of the iterated logarithm from 2 years ago in a way so that we can weaken assumption A2, so that small counts still will fit for this weakened version of assumption A2. And this is what we obtained. So the new assumption, which allows us to prove the desired law of the iterated logarithm, is the following. We assume that there exist independently, almost surely non-decreasing, stochastic processes phi1, phi2, and so on, which take values in set 0, 1, 2, and satisfy the following three conditions, A, B, and C. The first condition, A, is the main condition, and conditions B and C are just technical conditions, which we need for some technical reasons. So in A, we require that for time s smaller than t, the difference of indicators of events at t and s is absolutely bounded by the difference of processes phi k at time t and at time s. In the second assumption, we require that if you consider process y, which is the sum of those chosen sub-processes phi k, then the mean of this process y is finite for each given time t, we denote it by f. And the last condition is that the mean of original process x at time 0 does not exceed the mean of this new process y at time 0. So let's check why all of those assumptions indeed hold for small counts. To recall, the events ak for small counts were events that those Poisson processes were equal to j, and we suggest to consider the following processes phi k. Let it be the sum of two indicators. The first indicator is that there are at least j balls in the box, and second that there are at least j plus 1 balls in the box. Then we already know from previous discussions that those indicators are indeed non-decreasing, and that they take values in a set 0, 1, 2, because it's just sum of two indicators. So let's check all of those assumptions, A, B, and C. For A, we take s smaller than t, and we consider indicators that event ak of t holds minus indicator of this event at time s. Let's rewrite each of those indicators as the difference of two. So there are j balls in the indicators that there are j balls in the box is the difference of indicators that there are at least j balls and that there are at least j plus 1 balls. So with this at hand, we are down to prove that this module doesn't exceed the phi k at time t minus phi k at time s. And we prove this inequality in the simplest way possible. We just prove that what we have under the module doesn't exceed the right-hand side, and minus what we have under the module also doesn't exceed the right-hand side. I'll do only the first part of the proof because the second is exactly the same. Assuming that there is no module, we do not need to care about the first and third summons because they're the same, so they cancel out. Let's move the second summon to the right-hand side, the fourth summon to the left-hand side. So we are down to prove that indicators that at time t there are at least j+1 balls is not smaller than at time t, at time s there are at least j+1 balls. But it is true because it is exactly the statement that this indicator is not decreasing in time. So A holds. Then let's move on to B. We consider the process Y, which is the sum of those chosen subprocesses Vk, and we can see that it turns out to be simply the definition of the number of boxes containing at least j balls plus the number of boxes containing at least j+1 balls. So we want to check that the mean of this process is finite for each given time t. And the simplest way to prove it is to do some sort of root estimate. So the number of boxes containing at least j balls cannot exceed the total number of balls which were distributed. The total number of balls which were distributed is pi of t, so we have an equality which holds almost surely that this quantity doesn't exceed pi of t. Then the mean of this quantity doesn't exceed the mean of the Poisson process at time t, and this mean is exactly t. So the function f is bounded by 2t from above, which means that it is finite for each given time t. And the third assumption which we need to check that the mean of original process x, so mean of small counts at time 0, doesn't exceed the mean of process y at time 0, but it holds because both of those quantities are 0 for the reason that at time 0 nothing has happened in this Poissonized version of the scheme because arrival times for Poisson process are almost surely positive. It means that at time 0 no ball arrived and all of those quantities are 0. And with this at hand, of course, checking other assumptions which we had in the law of the iterated logarithm, I'm going to omit it because I do not have really time for this. We can move to the main results. So the final results after application of the previous general law of the iterated logarithm and then performing the Poissonization, we obtained the following three different laws of the iterated logarithm, which correspond to different regimes of parameter alpha, when alpha is from 0 to 1, when alpha is 0, and when alpha is 1. And I start from the case when alpha is from 0 to 1, because it usually is the easiest case to deal with, and it turned out to be the case for us as well. So assuming that counting function is regularly varying of index alpha from 0 to 1, we proved the law of the iterated logarithm for small counts, so that the upper limit of the small counts centered by their mean and normalized by such function is equal to 1 almost surely, and that the lower limit of this fraction is equal to -1 almost surely. And later I will not be writing anywhere results about lower limit anymore, but I still mean it, so keep it at the back of your head that it exists. The next regime we move on to is regime when alpha is 1. And here we need to separate two cases, when j is at least 2 and when j is equal to 1. The reason for that is the following. So when j is at least 2, all of those small counts are asymptotically equivalent one to another, just up to some constant. However, when j is 1, so the number of boxes containing exactly one ball is growing asymptotically larger than all of other small counts. That's why those two cases require different treatment. So first case, when j is at least 2, we again prove the law of the iterated logarithm for small counts. For j equals 1, we were not able to prove it under general setting, so that counting function is regularly varying of index 1. We needed to impose one little technical assumption, which is stated in terms of function L hat, which is defined as such integral. And we can show that this function L hat is well defined and finite for large enough t. So the result was, assuming that this technical assumption on function L hat holds for small enough positive gamma, then we proved the law of the iterated logarithm for small counts. However, if this technical assumption does not hold, then our proof gives only that the upper limit doesn't exceed 1, but the far...
Valeriya, I'm sorry. You write that one can show that L is well defined, but if L is 1, is just 1, this integral is divergent, or I don't...
Yes, but if we are in this setting, okay, let me go back. This counting function divided by t, it diverges to 0, like I showed somewhere in the beginning. So when alpha is 1, here slowly varying function L cannot be arbitrarily slowly varying.
It cannot be. I see, I understand.
But it should go
Thanks
to
a
0. Yes, that's why it's in particular well defined. Yeah, so back to Igor. If this technical assumption does not hold, a part where we find a subsequence along which the limit is exactly 1, it fails. So we actually do not know what happens when assumption 1 fails. We do not know because we do not have counterexample, nor we have the proof. It's still an open question. And the last regime we move on to is when alpha is equal to 0. So it means that we assume that the counting function is slowly varying at infinity. This regime is historically the hardest to work with because it turns out that this assumption is not enough to control in the way we want the behavior of all of those characteristics. That's why compromise approach is to assume that counting function is not general slowly varying function, but that it belongs to a subclass of slowly varying functions, which is called Deham class. So let me give you a definition. We say that function f belongs to Deham class pi if for all positive lambdas and some slowly varying at infinity function L, this limit relation holds. And let's look at a couple examples. So first, the function which is log of t, it belongs to Deham class pi, because if we count the nominator, we obtain there just logarithm lambda. So if you consider the denominator to be just constant 1, then this relation holds even without a limit, and we are good. However, if you consider the integer part of t, even though it is a slowly varying function, it does not belong to the Deham class because the nominator is bounded, but it does not have a regular behavior because of the presence of this integer part. So we cannot choose any function in the denominator, which depends only on t, which would make this limit relation to be true. And as I mentioned, it's known that every function from Deham class pi is slowly varying, and working with slowly varying function outside of this Deham class pi is a challenging task because we do not know even how the variance of the number of cuboid boxes behaves, let alone some limit theorems. For this case, when counting function belongs to the Deham class, we proved the following. So assuming that this auxiliary function L has two different regimes of behavior. The first, which we suggest, is that it behaves like logarithm to some power beta times another slowly varying function. Then actually what we proved is the law of the single logarithm. So small counts centered by their mean and normalized by this function where there is only one logarithm, has the upper limit, which is equal to some constant. If the slowly varying function exhibits such exponential behavior, then the law of the iterated logarithm holds. And another interesting open question here is the following. We considered only two possible behaviors of this auxiliary function, but of course it does not exhaust all of the possibilities. And it is interesting when does the phase transition happen in terms of this auxiliary function L from the law of the single logarithm to the law of the iterated logarithm. Thank you for your attention.
Okay, thank you very much for the interesting continuation of your previous investigations. And maybe somebody have questions or comments, please.
Yeah, maybe one question. So your assumption about P, about probabilities are quite general, and maybe it suggests the next possible step to study the random scenery as so P generated by, for example, stick breaking process, as Sasha used to do before often, or maybe by some in other ways. What do you think? Is it possible?
Of course, it is possible. I think at some point of my career I will get there, but now it's not in the priority. It's not in my PhD offer.
Okay, thank you.
I'd like to comment on Andrei's question. Actually, when you consider random probabilities, you obtain two sources of randomness, right? One source of randomness is coming from randomness of probabilities, and which is absent in the original Carlin scheme. Yes, and also the second source of randomness is randomness of sampling, which is present in the original Carlin scheme. But what we know so far is that randomness of probabilities always wins the randomness of sampling. So I mean, when investigating Carlin occupancy scheme with random probabilities, the information about limit behavior of just deterministic Carlin scheme gives no clues about what's happening with this Carlin scheme in random environment, or Carlin scheme with random probabilities. So the ideology and methodology is absolutely different. Yeah, so my message is that no results obtained for Carlin occupancy scheme in deterministic environment, so it doesn't give any consequences, any implications for the Carlin scheme in a random environment.
Yeah, thank you, I see.
Okay, other questions,
I have another sort of question. Thank you for your talk. It's very clear and detailed. It's really very interesting to see this new development and what you have done 2 years ago. My question is the following. So when you assume regular variation, you have, roughly speaking, equal probabilities. So meaning that they do not change much from, so if you order the probabilities in decreasing sequence, then they do not change much when you go to the next index. I mean, the quotient of neighboring probabilities is almost 1.
Oh, okay. Let's.
And that means that you roughly have sort of big blocks of probabilities which are roughly equal. Yeah. So, do you see any connection of this regular variation case with just classic situation where you have simply equal probabilities? Of course, finitely many equal probabilities. So, in the style of Kolchin, Sevastyanov, Chistякov.
Okay, I do not know any precise connections, but my intuition is that we expect it to be different because in the setting when there are finitely many possible boxes, sooner or later, like the number of occupied boxes will just become equals to the number of all boxes. And I don't know which sort of like loss of the iterated logarithm we can talk about later. Like if we know that it's almost surely will be just n.
Yes, that's correct. But you have a big series of boxes which are roughly equal, and the next series is smaller. So until sufficiently long time, you do not see the next series, and you roughly work with equal probabilities. That's the idea, and that's actually the way how you can create fluctuations. If you do not have regular variation, you have a big block of equal probabilities, and then a long block of probabilities which are much smaller, then you can create sort of waves and non-convergence of this singletons, doubletons, and so on.
Okay.
But,
So what
the
would you...
length of the block, Sasha, length of the block also must be controlled. So, do we have really the case of application of the Colchin results? Yeah.
Oh, yes, for certain. It's for certain you can create arbitrary waves by taking very long and blocks of very small probabilities. That's for certain. But in case of regularization, it doesn't happen because they decay very slowly, and that might be interesting to see the connection with the classic situation, how it embeds in this more general scheme. But anyway, thanks. I understand. Thanks for your
Okay, just to
answer.
summarize your questions that I understand it correctly. So outside of a setting when counting function is regularly varying, you suggest that since what we have will be split like into blocks where the probability will be approximately the same, we may try to reapply results from Kolchin, Sebastianov, and so on to look when counting function is not regularly varying, right?
Well, if the counting function is not regularly varying, you can construct with these long blocks any sort of fluctuation you like.
Okay.
This your K star will fluctuate with arbitrary waves without. You can create very strange things.
Okay.
Without achieving any limit. My question concerned connection of regularization with the classics, if there is some parallel. Using classics not to create sort of adverse behavior, but rather attack regularization from some more classic positions. That was my question.
Okay.
Okay.
Hello, Sasha. Nice to hear you.
Okay.
But do you mean that dealing with this restricted scheme, I mean, if we cut it somehow, would be easier than dealing directly with infinite scheme with infinitely many boxes?
No, certainly not. Certainly, the approach you apply is certainly the right one. My question was just to maintain some connection, to see maybe in depth what's going on there.
But what could be simpler than the sum of independent indicators?
Some of independent indicators we have the same, distribution.
Yeah.
Okay. I agree to some extent. Yes.
Okay, maybe we have such a fruitful discussion. Yeah, okay. Thanks everybody for participation of this first part of our meeting today. Especially thanks to our speakers for carefully prepared presentation, interesting presentation with new results. And for today, that's all. Hope to see everybody tomorrow again at the same time. We have a continuation of our small conference for young scientists. Thanks everybody, and bye.
Bye.